Welcome, students. Are you absolutely ready for tomorrow's test? You definitely are. Today, we're doing a rapid-fire walkthrough of 12th Chemistry Unit 8, specifically focusing on ionic equilibrium from the TOOT Guide worksheet sections 8.1, 8.2, and 8.3. I'm going to read the exact questions and chemical formulas line by line, exactly as they appear, but I'll break down the reasoning for you in the easiest, most conversational English possible so you totally get it. Let's get you completely prepared.
As you can see, this is TOOT Guide page 69 EM. This right here is the exact high-yield material you need to master for tomorrow's exam. We're skipping all the fluff today. If you clearly understand the exact questions and concepts on this specific page, you're practically guaranteed a top grade. So let's lock in.
Moving on to section 8.1.3, the Lewis concept. It's super straightforward. Lewis acids, electron deficient. Lewis bases, electron rich. Let's break that down simply. Lewis acids are electron deficient. That means they are hungry for electrons. They need them. Think of things like BF3, positive metal ions like Fe3+, or carbonium ions. They will always accept electrons. On the flip side, Lewis bases are electron rich. They have extra electrons just sitting there, ready to be generously donated. Examples: NH3, negative anions like F-, or carbanions. Just remember this golden rule. Acids accept, bases bring. Keep that in your head, and the core concept is completely clear.
Okay, let's look at question number 5. When aqueous ammonia is added to CuSO4 solution, the solution turns deep blue due to the formation of tetraamine copper II complex. CuH2O42 plus 4NH3AQ equals CuNH342 plus AQ. Among H2O and NH3, which is stronger Lewis base? Ants, stronger Lewis base is H2O. So why is water, H2O, the stronger base here? Well, a Lewis base donates electrons, right? In an H2O molecule, the oxygen atom has 2 lone pairs of electrons ready to be donated. But in ammonia, NH3, the nitrogen atom only has 1 lone pair. It's a simple numbers game. The more extra lone pairs you have available, the stronger the Lewis base you are. Simple as that.
Next up, pay attention because this is a previous year question from September 20. Question PY2. Classify the following into Lewis acids and Lewis bases. A, BF3, B, CO2, C, MgO, D, CH3-. If you look at the answers, BF3 and CO2 are in the Lewis acids box, while MgO and CH3- are sitting in the Lewis bases box. But why? Well, we just learned this. BF3 is famously electron deficient. It desperately needs electrons. CO2 has polar double bonds, making it eager to accept electrons too. So both act as acids. On the other hand, MgO is a metal oxide, which naturally makes it electron rich, and CH3- is a carbanion carrying a negative charge, meaning it can easily give away extra electrons. That makes them bases. Make sense?
Here's another previous year question, this one from June 23. Question number 7. Which of the following fluoro compounds is most likely to behave as a Lewis base? A, BF3, B, PF3, C, CF4, D, SiF4. The answer is B, PF3. It's actually really easy to see why PF3 acts as a base here. You just need to look at the central atom. In PF3, the central phosphorus atom has a non-bonding lone pair of electrons just hanging out. Because that lone pair is there, it can freely donate electrons, and since it donates, it behaves as a Lewis base.
Now look at these previous year tags: August 22, June 24, and June 25. This is a highly repeated question, guys, so you absolutely must know this. Question number 8. Which of these is not likely to act as a Lewis base? A, BF3, B, PF3, C, CO, D, F-. The answer is A, BF3. If we use simple elimination logic, this is a breeze. We already know for a fact that BF3 is an electron-deficient molecule. The octet on its central boron atom is incomplete. Because it's deficient, it has to accept electrons. And what do we call an electron acceptor? A Lewis acid. Therefore, a Lewis acid like BF3 can never, ever act as a Lewis base.
Moving on to section 8.2, strength of acids and bases. Strong acid, completely dissociated in water, HCl. Weak acid, partially dissociated in water, H3COOH. Let's get these rules straight in our heads. It all comes down to the Ka value, which is the ionization constant. If an acid completely breaks apart in water, it's a strong acid, and its Ka value will be strictly greater than 10. If it only partially breaks apart and holds on to its ions, it's a weak acid, meaning its Ka value is going to be less than 1. So remember, Ka greater than 10 means strong, Ka less than 1 means weak.
Here's another previous year question from March 20. Question number 9. The aqueous solutions of sodium formate, aniline chloride, and potassium cyanide are respectively A, acidic, acidic, basic, B, basic, acidic, basic, C, basic, neutral, basic, D, none of these. Ants. B. Let's quickly demystify how we got that basic, acidic, basic sequence. It's all about salt hydrolysis. Both sodium formate and potassium cyanide are salts formed from a weak acid and the strong base. Because the base is stronger, the resulting solution is basic. But aniline chloride is different. It's a salt made of a weak base and a strong acid. Here, the acid is stronger, so the result is acidic. Basically, whichever parent is stronger wins the chemical tug-of-war.
Almost done. Section 8.3, Ionization of water. This has a previous year tag from September 20. Question number 10. Define ionic product of water. Give its value at room temperature. The immutable formula here is Kw equals H3O plus OH minus equals 1 times 10 to the power of negative 14 at 25 degrees Celsius. To keep it short and sweet, the ionic product of water is just the concentration of hydronium ions multiplied by the concentration of hydroxide ions. And at a standard room temperature of 25 degrees Celsius, this value is strictly 1 times 10 to the power of negative 14. You need to have this specific formula and that tiny number locked in your memory for tomorrow's exam.
All right, let's wrap this up with tomorrow's test prep summary for worksheet sections 8.1, 8.2, and 8.3. We've reached the end of this targeted prep session. Let's recap the big hitters. Lewis acids are your electron-deficient acceptors, like BF3. Lewis bases are your electron-rich donors with extra lone pairs, like NH3 and H2O. Strong acids will completely dissociate in water, boasting a Ka greater than 10. Weak acids only partially dissociate with a Ka of less than 1. And finally, never forget the ionization of water. Kw equals 1 times 10 to the power of negative 14. You now have the exact formulas, the previous year references, and the clear reasoning behind every single answer. It literally doesn't get any easier than this. So, are you ready to walk into that exam hall tomorrow and bag a perfect score? I know you are. Good luck!